So welcome to part 5 of this lesson on economics, and this is going to be all about trade. Now we can define trade as arbitrage of spatial and temporal variability in the Earth's resources. So what do we mean by that? Well, arbitrage is about taking advantage of price differences in different locations and eventually evening them out. So, for example, oranges grow well in Spain, but not in Scotland. So what an entrepreneur can do is buy oranges in Spain, where they're abundant and cheap, and sell them in Scotland, where they're rare and expensive, and make a profit on the price difference. But of course, the more they do that, the more oranges they ship from Spain towards Scotland, the more oranges become available in Scotland and the price will fall by the law of supply and demand. So by taking advantage of those price differences, they will cause the price differences to even out. And if arbitrage is taken far enough, you'll end up with equality in the prices, or at least give or take the cost of transport. So when we say trade is about arbitrage of variability that's spatial, that's basically what I've just been talking about. If you've got oranges in Spain but not in Scotland, and salmon in Scotland but not in Spain, then you can arbitrage that difference, that spatial variability in resources, that you get oranges in one place and salmon in the other. You can arbitrage that and get oranges to Scotland and salmon back to Spain. And so Spain ends up with both oranges and salmon, and Scotland ends up with both oranges and salmon. This is necessary because otherwise a society would be limited to the most scarce resource that it has in its local area. So if, for example, you've got enough wheat to feed 1,000 people,
but only enough cotton to clothe 10 people,
then you can't have 1,000 people. You're going to be limited to the 10 people that you can clothe. But if you can trade, arbitrage of variability, so that you can give some of your wheat to people who are short of wheat and take some cotton from people who've got lots of cotton, then you've arbitraged that difference, and you can support a higher population, maybe 500, because you've given away 500 people's worth of wheat and you've imported 500 people's worth of cotton. And so instead of being limited to the 10, you can have a much larger population. So that's arbitraging variability, or spatial variability, I've just been talking about. For temporal variability, there's feast and famine. There's a harvest time when food is abundant, and a lean time when it's hard to come by. And you may have famine years, for example, when for the whole year there's very little food around. Well, you can arbitrage that temporal variability of times when you've got lots and times when you've got little, by at the times that you've got a rich, bountiful harvest, the weather's been particularly good, you can sell your excess, and then at another time, a year or two later, when you've had a bad harvest, you can buy back. So you're arbitraging the temporal variability. You're less susceptible to the variability over time in the resources available to you, because you're able to trade away your glut and then buy in to cover your deficit. And if you didn't do that, then again you would be limited to what the population you could support in the leanest years. So if you knew from experience that in times of abundance you could support 1,000 people, but in times of famine and scarcity you can only support 100, then you would have to limit your population to 100. And if you didn't, it would be limited anyway, because when the famine comes along it will wipe out all those who are above that number. So again, arbitrage, temporal arbitrage, allows you to support a higher population than you would without it. So there is the logic of trade. It's about arbitraging variability, or spatial and temporal variability, in the Earth's resources. Now, arbitraging of spatial variability can be done just by simple barter, because you've got oranges, they've got salmon, you swap, barter. But temporal variation can't be done in that way, because you haven't got anything to exchange. The point is you will have something to exchange next year when the harvest is better, but you haven't got anything to exchange now. So this requires debts, IOU, money, all those sorts of things. So you get in food now and you owe those people. And then later, when they have a famine, then they can come and claim some food back from you. So this means you've got to have some means of remembering those debts if it gets complicated enough. It couldn't be, you know, like modern money, but in the past it might be things like gold nuggets that people desired and were happy to accept in return for, you know, for something more tangible like food, something more useful. And then you can exchange that gold back. Or it could be more arbitrary things like beads that people have made up, and they're just a way of remembering debts. And this kind of trade goes back a long way. People have been arbitraging the spatial and temporal variability in their resources for an awfully long time, back in the Stone Age, certainly spatial. And sedentism, that is when people settled down, this caused trade to become more important, because in the past, when people were nomadic, hunter-gatherers wandering around across the landscape, they could arbitrage spatial variability and temporal variability by just moving. So if they were in a place where, you know, there was nothing to eat, they just walked down the coast to find where there was something to eat. But when people started to settle down into villages, then that was not a strategy available. They were very much restricted to what they could produce in their local village, local area. So they had to engage in trade to cover these problems of spatial and temporal variability. And also this led to people being able to have possessions more. When you're a hunter-gatherer moving around the landscape looking for berries and rabbits, you don't want to carry too much on your back. So you don't have many possessions. You don't take a cup with you, you just use your hands to drink from the stream. But when you're settled in a village, then you can amass possessions. You don't have to carry them around, you just need to keep them in your hut. So this also means then that ownership of these possessions and of these resources also becomes more important. So you start to worry more about, this is my field. And so it leads to the kin-based or tribal cultures of, particularly of the Middle Old World, that we talked about in the module on cultures and civilizations, because you're more worried about ownership. So you're not going to share things with strangers, and you're also worried about inheritance, because if this is my field, then I want it to pass down to my children, because I'm concerned about how they're going to survive. So these kin-based and tribal things start to emerge through sedentism. Okay, so different parts of the world are connected through trade, and this has been the case for a very long time, certainly since the beginnings of farming, and indeed even before that into the Old Stone Age. And you know, even the Romans traded with China and India. And what I'm going to do is draw up a map of the world in 1000 and show on it the kinds of trades that existed in that time, so 1,000 years ago. Okay, so this is a chart of main centres of world trade in the year 1000 and the kinds of things that were traded between them. And this isn't complete, but just to give an idea. So, for example, Eastern Europe was selling slaves and furs into Western Europe and receiving swords in return. Western Europe was selling slaves into the world of Islam and receiving spices from the world of Islam. Africa was supplying slaves to the world of Islam as well as gold, and receiving in turn textiles and swords. South Asia, India, was receiving iron from Africa and sending textiles back. There was spices going into the world of Islam from South Asia. Silk from East Asia, so silk from East Asia was going to Central Asia, South Asia and Southeast Asia, and in return it was receiving horses from Central Asia, textiles from South Asia, and perfumes and spices from Southeast Asia. Oh, and I've also got here porcelain, selling porcelain into South Asia. And paper was another product coming into Europe from Central Asia, ultimately from East Asia. So that just gives an idea of the kinds of trades that were going on in the year 1000. It was clearly a very active system. And it is a system, and we can sort of demonstrate that by considering the connectivity of the different nodes. So we can see here that Islam emerges as very much the hub of this network. It is connected directly to every other region, whereas Africa was not very well connected, nor was Western Europe, nor Southeast Asia, hanging off the ends here. And we can plot a rank size plot, double logarithmic scale. So there's rank along there, and we'll call it node degree. So here we're using concepts we covered in the mathematics module, the idea of a rank size plot to show a power law and the degree of a node in a network. So that's just really the number of links to each node. So Islam is the rank 1 up the top, and if we plot the node degrees of all the others, they actually fall on a straight line pretty much. So it's a power law, meaning that this is a log-log plot. This is the logarithm of rank and logarithm of node degree. But anyway, so we get a power law, and that suggests then that it is a system. There is a leader within the system and everything else slots into place behind it. If they were more evenly spread, then it wouldn't be a system. Each one would be more a thing in its own right and just trading with peers. But in fact, Islam leads this system and the others are arranged in a hierarchy behind it. And while we're on this subject, the volume of world trade has just increased through time. So even over the course of the 20th century, it's said that it's gone from 5% of gross world product. So trade 1900 was 5% of the gross world product. the total economic output of the world, and today it's estimated at 25%. So trade has become, which was already a large part of world product even back in 1900, but it's today a huge part of it. And so we live in an increasingly connected world, and with all the consequences of that we're living in each other's pockets much more than we were. Okay, I'm now going to say a bit about trade routes. Now, this is a simple but useful diagram to bear in mind, which shows the main trade routes going back through history. So there were 4 key centres of trade: Europe, China, East Asia, India, South Asia, and the Middle East. And then after the discoveries of Columbus, post 1500, America joined the system. And as I've put here, the connection between Europe and East Asia was a land route, the Silk Road, and the connections around here were largely by sea. And of course the connection to America was across the ocean. And this is sort of got an echo today with China's Belt and Road initiative. The belt is the land route across Eurasia, and the road is the maritime road around the sea route. So it involves constructing railways for the land route and ports for the sea route. And what we noticed in this is that Africa isn't part of the system, not until very recently, because Africa was always a difficult continent to penetrate. It's separated off by a great desert, and disease and jungle, inhospitable conditions made it very difficult to penetrate. And it's because it's a vast landmass, so there's not much access to most of it by sea. Particularly when in earlier days before Columbus, people couldn't, go very far by sea. Okay, let's now take a look at the evolution of some trade routes. This is based on the description of Northcote Parkinson. So we can start. We had in ancient times, there was trade across Eurasia, connecting Europe to China and South Asia. So that's in ancient times. And then with the time of Columbus, we had trade from Europe to the Americas, and also round the Cape of Good Hope into India, thanks to Vasco da Gama. That was Columbus first, and then Vasco da Gama. And then when Spain conquered the Philippines, which can add off here some of these islands. So the Philippines, and Spain conquered the Philippines, it established trans-Pacific trade to the Americas, from Spanish colonies in the Americas to the Spanish colony in the Philippines, joining those two parts across the huge Pacific Ocean. Then in the 18th, 19th century, the Mississippi became an important trade route, connecting the Atlantic and hence the world's trade system into the heart of America. And then later in the 19th century, there was the transcontinental railway going all the way across the US. Should put the Mississippi. Well, let's say this is the 16th century. This about 1500 with Columbus and Vasco da Gama. Mississippi, say 18th, 19th century. The Transcontinental Railway, 1869, was completed, and also at the same time, the Suez Canal. Suez, 1869, completed. So connecting across that vast landmass and connecting the Mediterranean to the Indian Ocean system. And then the sort of latest big development was the Panama Canal. In 1914. So through these different major innovations in routes, world trade has grown. Okay, now the theoretical historian Andrew Bosworth has divided the growth of world trade into 6 architectonic orders, as he calls them. Centered around major trade hubs going back to 3000 BC. So he suggests that world trade has always been structured by big cities, and though which cities were part of the interconnecting trade routes has varied over time through 6 architectonic orders, and those have overlapped to some extent. So I won't go through all 6, but I'll cover 2 of them. I'll cover 4 of them, so we'll just compare 2 different architectonic orders now, and then I'll compare another 2 in a moment. So I'll just draw them up first. Okay, so here are 2 of Bosworth's 6 architectonic orders, and I've left out a link, haven't I? So global trade is an expensive operation to load up ships, transport goods long distances with all the dangers and risks involved of shipwreck and pirates and what have you. So only the richest, biggest cities can afford it. And so they become the hubs in these spoke systems, hub and spoke systems, serving their regions and then interacting with each other in a higher level global network. And Bosworth says that the cities that have formed this network have changed over time. For example, due to climate change, due to political changes in different parts of the world, due to innovations making some regions rich. For example, iron coming in to replace bronze, changed the where the world's wealth was distributed, and changes in transportation technology that have changed the significance of geography. So those and maybe many other factors have tended to reshape where the best place is to have your trading hub. So back in, he says, 1500 BC to AD 1, these were the major cities of world trade, and this is how they were connected. But then from 200 BC to 1350, these were the major cities of world trade. So back in 1500 BC, we've got the Phoenicians in Carthage and the Minoan civilization of Knossos. And but later on, from 200 BC, we've got Rome and Byzantium emerging. So, you know, changing cities there in Europe and also all across Eurasia. And what we can see as well is that these overlap. So it wasn't a flick of a switch and you suddenly went from that to that. Of course, this declined and this rose. So these cities gradually faded away as these cities came up, as the logic changed. And you can imagine how that is going to be a driver of Eurasian history as one global trade network starts to fade and another starts to come in. So that's two architectonic orders, and now we'll take a look at two more recent ones. Okay, so here are Bosworth's two most recent architectonic orders, from the discoveries of Columbus to around 1900, an Atlantic system. So the cities of New York, Mexico City, Havana, Bahia, Lisbon, Seville, Le Havre, Amsterdam and London, all distributed around the Atlantic. This was where the engine of world trade was. Arbitraging these differences in the world's productivity and resources between the Americas and the old world Eurasia. And since 1900, he says there's now been a shift to a Pacific-based global system. So in fact, I've shown these links right across the world, but they're really across the Pacific. So now cities like Vancouver, San Francisco, Los Angeles on the west coast of America, not the east coast, and the cities along the western side of the Pacific, or the east side of Eurasia. So Sydney, Hong Kong, Shanghai and Tokyo. And I should have said, though it's perhaps fairly obvious, that the shift from the Atlantic-based architectonic order to the Pacific global architectonic order was accompanied by major upheavals in the world, as some cities and regions declined and other cities and regions came up. And now we're going to think a little bit about protection of trade routes. So trade routes attract bandits, pirates, preying upon the goods that are flowing through across the landscape and not necessarily very well protected. So what then? So the trade can be is hindered by bandits and won't get through if bandits are too much of a problem. And what happens is you then get governments who keep down the bandits, and those governments expect to extract taxes and tolls on the trade for providing protection against bandits. And this protection can be something of a protection racket, in that the governments really evolve out of the bandits. They are just basically doing the same thing, saying, well, pay our taxes and tolls or we'll just take it anyway. But although it's perhaps a bit disparaging to say that it's just a protection racket, it's more predictable. That's the key innovation of governments. It's not that they don't take your goods, but it's more predictable and also more proportionate. So yes, they'll extract a bit of blood from you, but not enough to kill you, whereas bandits don't really mind if they kill you. But governments want to keep the trade flowing, so they make this more, relatively painless. At least it's proportionate to what is reasonably affordable. Now, theoretical historian Malkoff has done a model of trans-Eurasian trade, in other words, really of the Silk routes, a mathematical model. And his idea is that trade is about what we said at the beginning, arbitrage across variability in from places where price is low of a good to where prices are high. So trade is about arbitraging between the difference in price between two places. So in the Southeast Asia, spices were cheap. They grew on the trees, there's plenty, they were abundant. Whereas in Europe, medieval Europe, spices had attracted a high price. So when many of them, but they were very desirable. So the Silk Roads were driven by the difference in price. And the trade then changed the balance of prices, because the more effective price was, so the more effective trade was, it brought down this price and created the demand transfer to here. The sellers no longer had gluts, they were serving this market, so the price here would start to come up, so they would start to balance out. And Malkoff's basic equation of his model is that the rate of change of price dp by dt, and it's a partial differential because price depends on time, it changes over time, but also depends on space where you are. So we said that here says low, here says high, so price depends on where you are in space, but also through trade the low prices can come up and the high prices can go down, so it depends on time as well. So it depends on both things. So this is a partial differential with respect to time, and that is equal to the constant gamma times the Laplacian, as I pronounce it, grad squared, whoops, let's put another constant in front of it, grad squared of the price minus the production, and there's a constant gamma in front of it. So what is this saying? Well, the grad squared P is the gradient in the price. It measures the differential in price. In fact, it is not just the differential in price here. It is how the price is varying through that. So it's from here, there's the lowest price. Oops. Low price and high price. So whether trade flows through here depends on there being a difference between the price before and the price after. So long as there's a price difference between those two, then trade will be flowing through this intermediate point, and that's why it's grad squared. It's differentiating it twice, because it's not the change from there to there you're interested in. It's whether it's the difference in the change from there to there and the change from there to there. So that affects whether the price is changing, because if the difference between there and the difference between there and there are the same, then the goods will just flow through at a particular rate. But if it's changing, it's the differences in price are getting stronger or larger, then the trade flow from here to here will be weaker than the one from here to here. Because if this is a bigger price difference, there'll be more trade because it's more attractive. Whereas if this is a fairly small price difference, trade will be slower. So the slow trade in here causes less to be coming in than is flowing out, and that will change the price, put the price up more quickly, because it's becoming more scarce here. So we're interested not just in the delta from there to there, or the delta from there to there, but the delta of that delta versus that delta. So it gives us the grad squared. And it's saying that, such as I really just explained, if there is such a gradient in the price difference across a particular point, then that will make the price change, either increase, as in the scenario I just described, or if the differences were the other way around, it would decrease. If this price difference was bigger, then trade would be, or the goods would be flowing in here, and if this was a small difference, they wouldn't be flowing out so quickly, so the price would be falling here. But another thing that affects the price difference, or the rate of change of price, is production. So if here you are manufacturing whatever it is, porcelain, then that is going to bring the price of porcelain down. So Q is the local production. So, as I say, this is then his basic equation to describe how price varies at a particular point. And it's derived really from the physics of diffusion of gases, explaining why the concentration of gases changes, or modelling how the concentration of gases changes as they diffuse. And this is basically what's happening here. Goods are diffusing across the landscape in response to price differences, the same way that in physics gases, or things in fluid, diffuse in response to gradients, differences in concentration. And what Markov does with this equation is he creates basically a cellular automaton. So he divides Eurasia, and I should have drawn this probably as a grid, but they're supposed to be the same size cells. He divides Eurasia into a grid of cells, and then he considers the price in each cell, and it varies according to this equation, so that it depends on what's flowing in and what's flowing out, and that depends upon the pattern of prices in all the cells around it. And he then takes into account, and this is implied in this gamma and this K diffusion constant, he takes into account things like terrain. So it's easier to flow across, downriver, for example, than it is across deserts or mountains. And but he also takes into account protection. So he feeds into his model the changing patterns of empires in Eurasia, and suggests, or models the idea that where there are effective political authorities, powerful empires, then trade flows more easily, and where there is a lack of political authority, and therefore lots of bandits, trade finds it more difficult to flow. And he then follows where the concentration of trade flows through this landscape, given these variations in trade, as variations in terrain and political authority. And what he finds is that the flows through his grid of cells match the historical records for where the Silk Roads were. And as empires came and went, the Silk Roads changed, and his model picks up the same variation in the Silk Roads, reflecting the changes in political authority and therefore in protection of trade. Okay, we're now going to take a bit of a deeper dive into the evolution of trade routes through history. And there was an online blogger who calculated the lengths of the world trade routes over time, so the total length of trade routes at various points in history. And that makes it possible to plot the evolution of trade routes in terms of their total length. And that's what this plot shows. And notice that's a logarithmic scale. And the blog also recorded which routes were land and which were sea, which makes it possible to plot the fraction of trade that was being carried by sea over time. And that's what this plots here. And unfortunately that blog has gone now, but it's still possible to find the site on the Internet Archive's Wayback Machine. So what we can see then in terms of the total length of trade routes over time from 4000 BC to AD 2000 is that it's a straight line on a semi-logarithmic chart. So in other words, it's an exponential growth. And the black is the trend and the blue is the actual data. So we also see that there has been some fluctuation around the trend. So sometimes the trade route has gone below the trend and sometimes it's swung above. So there's been kind of recessions in world trade and booms in world trade, fluctuations over time. And in terms of the sea fraction, we also see that there's been a tendency, this is not a logarithmic scale, it just goes from 0 to 1. There's a tendency for the fraction of trade that's carried by sea to increase over time. And again, there have been some fluctuations. It's about 0.5 in fact, so this scale is a little bit wonky, but this is about half is carried by sea. So the question is, what explains these fluctuations in world trade above and below the trend? Well, one explanation is due to the archaeologist Andrew Sherratt, who suggests it's related to shifts in world trade, like Bosworth's shift in architectonic orders. And he gives the example of the city of Petra in the Jordanian desert, which was once a very beautiful, rich city and is now just a ruin in the desert. It grew rich on trade passing across the land route, but across the desert through Petra, but it was eventually bypassed by the Indian Ocean route, and so trade there declined. So the whole trade route collapsed and was replaced by a shorter route. So this can the shift from one trade route to another could cause a depression in the growth of world trade routes. That's Sherratt's idea. Then Bosworth himself talks in terms of blockages. Okay, so here are Bosworth's examples of blockages in Trans-Eurasian trade, world trade. So the columns show what the blockage was, how people got around that blockage, the circumvention, and which cities were responsible for constructing the circumvention, the alternative route around the blockage. So the first blockage around 25 BC, Parthia, so roughly in the region of Iran. They blocked the Silk Road, the Trans-Eurasian trade. So the Romans responded by developing the Red Sea route. So they didn't go by land to India now, they went round through the Red Sea. And the cities involved with that were Rome, of course, at one end of the route, Alexandria in Egypt, so the route from the Mediterranean into the Red Sea, and Anuradhapura at the other end in India. Then around AD 550, Persia blocked the Silk routes, the Trans-Eurasian land routes. And this time it was Constantinople, the Eastern Roman Empire, or what people call the Byzantine Empire, so this says Byzantium. Byzantium responded Byzantium on the Black Sea, where Istanbul is today, Turkey. So Byzantium developed the northern steppe route. So while Persia was blocking the southern route, so across Iraq and Iran to India and China, Constantinople responded, the Byzantine Empire responded by going around the north of Eurasia, the northern steppe route. And so the key cities of that route were Constantinople at the Byzantine end and Chang'an in China. Then in around 800 to 1100, it was the northern tribes in China, the barbarian tribes, who caused trouble, and the bandits, so they made trade impossible. So the Song dynasty of China responded by resorting to maritime trade, a bit like the Romans did with the Red Sea. So they started going from the South China Sea into the Indian Ocean to get round these bandit tribes in northern China. And the cities here, Hangzhou, Canton, and then Cairo at Egypt and the end terminus of the Red Sea, and then into the Mediterranean. And then lastly, in the 1400 to 1500, the Muslim powers, the Ottomans, blocked the trade route from the eastern Mediterranean. So it again was no longer possible to travel by land across Eurasia. And the Europeans responded by finding the Cape route round the Cape of Good Hope, round the bottom of Africa, and then so down the Atlantic, round the bottom of Africa and up the Indian Ocean to India and Southeast Asia. So that was a response to this blockage, but in the course of it, and in fact before they found the Cape route, the Europeans crossed the Atlantic because, as the story goes, Columbus thought that he could get to East Asia by sailing west. And he bumped into the Americas on the way. So the cities here then were Lisbon, Seville, Amsterdam and London that drove this trade, because they were seagoing as well. The ships went out and brought things back, so they did everything for themselves. So it was mainly the cities of Europe that developed rather than a terminus in the eastern and southern Asia. But always these interventions, circumventions were driven by cities because, as we said, world trade is structured by the big cities. They're the ones that can afford the investment needed to establish and maintain trade routes. And then Peter Turchin explains these fluctuations in terms of pandemics and political disruptions. So we'll be coming on in a later module to Turchin's structural demographic theory about cycles in stability and instability in societies, and these lasting several centuries, so that every few centuries they go through crises and fall into periods of disorder. And what Peter Turchin then suggests is that when societies that are at the ends of trade routes collapse into disorder, then the trade routes will collapse as well, because there's political turmoil and economic decline in these cities, so they won't be able to sustain the trade, so the trade will collapse. And pandemics, he suggests there that as populations start to trade and trade is flowing between them, then also pathogens or diseases can flow along the trade routes. So and because the populations have not been in contact before, the diseases of this population will be rather deadly to those ones, and they won't be used to them, and vice versa. So as they come into contact, pandemics spread, cause disease and population decline, and with fewer people there's less of a driver for trade, so the trade route will fall back and maybe collapse. And then the populations become isolated again, they can recover, and then they grow up again and start to come back in contact, and the cycle repeats. And Turchin has constructed an index of the connectivity of Eurasia over time. So let's have a quick look at that. Okay, so this is Turchin's index of connectivity from 200 BC to around 1800. And what he does is he takes the atlas at various time points and calculates how many countries you would go through if you started a journey on the east coast of China and just walked across or moved across Eurasia to the eastern Mediterranean. And he suggests that if you go through only a few countries, then Eurasia is well connected, whereas if you go through lots of countries, then it's fragmented into many smaller countries. And for his index, he takes the reciprocal of the number of countries that you go through, or empires. So if it's just two societies, countries, empires that you go through, then the index of connectivity is 1/2. If it's 3, it's 1/3, 4, 1/4. So the more countries you go through, the smaller the index, and that's what this is plotting. And he finds these are, correlated with events in history, so that 1300 here, this corresponds to the Mongol Empire, which connected most of Eurasia, and was followed by the Black Death, and centuries really of disease, and was only eventually started to recover around the 19th century with the beginning of the European colonial empires. So illustrating his point here. And he can also correlate these with cycles of stability and instability in the societies at the ends of the trade routes. So for example, the 17th century here, a time of low connectivity, is sometimes known as the age of crisis, or the world crisis of the 17th century. So that's reflected here. It was a time of disruption and instability throughout the world, in Europe and in East Asia. And Turchin notices that in earlier times, his structural demographic cycles, that were lasting several centuries, were not particularly synchronized. Those in China were occurring at different times to those in Europe, but in more recent times they have become synchronized. So as population increases at one end of Eurasia, so at the other, as the societies then fall into disorder and crisis, then that's happening together at both ends. And he suggests this synchronization, increasing synchronization that you can see, shows the increasing global connectivity. So what's shown here, although there were these fluctuations, there is an overall tendency for the world to become more connected over time. Now, I should have said about Turchin's index of connectivity that he also finds that these peaks of integration, we can call it, a high degree of connectivity across Eurasia, these peaks of connectivity integration are correlated with peak trade. So trade was strongest during these times when Eurasia was more politically unified. And that's in line with Malkoff's ideas that when there are effective political authorities, they facilitate the transit of trade because they keep down the bandits who otherwise make trade difficult. Okay, now I'll say a few words about cities and ports. So we've already seen that cities are hubs of global trade. They are the key nodes in the network. And as we said, that's because maintaining world-spanning trade routes is an expensive pastime, and but it's also a lucrative pastime. So it's only rich cities that can do it, and cities that do it will become rich. And cities can grow rich on trade alone. So examples are Hong Kong, Singapore in today's world. And in fact, it's often the case that cities that, or places that don't have very rich resources actually become rich through trade, because they have to engage in trade if they want anything, because their own location has very little to offer. So they become expert traders, and then they become rich on that. So having trade is often better than having rich natural resources. And the cities that engage in trade are often ports on the sea, and that's because it's easiest to move around by sea. And it was in the past, you know, a ship just floats and can carry, you know, large cargoes much more easily than carts travelling along dirt tracks. So so if you're a port, you're connected into that global highway of the sea, and once your ship has left port, it can go anywhere in the world very easily, just floating around. So trading cities are often ports, and as a result, these ports, through their trade, become rich and powerful, and that means they can be independent. It's difficult to dominate them because they are rich and powerful. But how independent they are depends upon the state of the land-based states or empires that surround them, whether those are weak or strong. So depending on the land-based empires, let's say, if they are weak, then ports are very powerful, because the land-based empires are weak, they can't dominate them. And in such a case, as some people use the term trading ports for them. So the trading ports are powerful city-states. They may be even city empires. They may have empires of their own, but they're very powerful because they're not dominated by land-based empires. And when, though, the land-based empires are strong, then the ports still somewhat independent, but they're more kind of protected by the land-based empires, and used as kind of neutral zones where empires can meet. And in such cases, they are known as ports of trade. So just to mention that terminology in case it comes up. Ports of trade. So here they are, you know, they're not the centres of empires themselves, but they are neutral zones between empires. And they can survive like that because neither empire can absorb them, because if one empire tries to absorb them, the other empire will try to resist that. So they become, as I said, neutral zones between empires. And the proportion of ports in the world's largest cities has increased through time. So ports as percentage of the 25 largest cities has increased from 20% in AD 1000 to 80% today. So that very much correlates with what we saw earlier, the growing fraction of trade that is carried by sea. So ports have become more important in the world. And now a few words on trade and culture. So if you are a merchant trading around the world, you need to have a capacity for mathematics to do your accounts. You need to have a rational approach to life so that you can check whether you're making profits and whether these trades are worthwhile, whether the risks involved are manageable, whether you have got fallback solutions and so on. So you need to be a very thinking, rational person in order to be a trader. And also, if you're involved in trade, you're communicating with other cultures, other societies, so you're exposed to new ideas. So cities that are involved in trade networks are characterized by these two things, a sense of reason, rational behavior, and exposure to new ideas. And so this means that trade, strong trade in a place, tends to encourage things like science, reason, new ideas, and humanism, things like freedom, personal freedom, democracy, values like that. So trade can affect the culture of a place. And Rashevsky, the mathematical historian, says that because ports are important centres of trade, then that would imply that the more ports a country or region can have, i.e. the longer its coastline, then the more advanced its culture will be. So we should expect the coastline of a country to reflect its level of cultural development. That's Rashevsky's argument. Just to repeat, because coastlines mean ports, and ports mean trade, and trade means cultural development. Okay, we're now going to consider a model by Rashevsky of how the size of a city, the population size of a city, depends upon trade. And this might be of interest, for example, because we know that where terrain is more difficult to cross, mountainous regions, for example, trade will be less, as modelled by Malkoff. And that might be reflected in the maximum size of cities. So that's what Rashevsky is interested in. And I'll sketch the basic setup. So there is a city serving a hinterland of farmers. And the city contains artisans who produce city goods that they supply to the farmers, and the farmers provide produce in return to feed the people in the city. And besides the artisans, the city also contains traders. Those are the people who take the city goods out to the farmers and then bring the farmers' produce back into the city. So we say there are N farmers in total. The size of the hinterland is of radius R, and the population of the city, NC, is equal to the number of artisans, NA, plus the number of traders, NT. And we want to find out how these numbers NC and N depend upon the parameters that describe this trade. So the first thing that Reshevsky says is that the number of artisans is related to the number of farmers by this equation, NA equals sigma times N. And this is saying that a given artisan can supply so many farmers, so the needs of so many farmers. So the number of artisans is related to the number of farmers. The more farmers, the more artisans you need. You need so many artisans per farmer. So that's what this is saying, NA equals sigma N. And then he's interested in the number of trips per unit time that the traders can make. So they're taking these goods out and bringing them back in. How many trips can they make? Well, the time for one trip is going to be the distance travelled
divided by the speed.
Now, we say the typical time, the typical distances correspond to the radius of the hinterland. That's to simplify. We might add a constant or something there, but just to keep it simple, the distance of the trip is related to the size of the hinterland, R. So, and it's going to be 2R because they go there and back. So the distance travelled is 2R divided by the speed to get the time taken. So that's the time for a trip. So the trips per unit time is just 1 over that. It's going to be V over 2R. And next we're interested in the amount of produce that's reaching the city to feed it per unit time. Well, there are N traders carrying this produce or fetching this produce, and each one is making this number of trips, V over 2R, per unit time. So that's a total number of trips across all the traders per unit time. And we're interested in the amount of produce they bring in, so we also multiply that by the load, the amount of produce they bring in one trip, what they can carry in one trip. So the number of traders times the number of trips they're making per unit time times the load, the amount of produce per trip. And for convenience, Reshevsky defines W as equal to V times L. So it's the speed times the load. So we can then write this as NT into W over 2R. And then he suggests that a farmer produces P amount of goods or produce per unit time, and he gives kappa, a fraction kappa of his produce into this trade. So he's prepared to pay a fraction kappa of his total production for the city goods. So we say the farmer produces P per unit time and trades away kappa P, a fraction kappa of his total produce. So from this perspective, the produce to the city per unit time is equal to the number of farmers. He's producing P per unit time, he's giving away kappa, so it's the number of farmers times kappa P. And so we can then equate these. So this is what the traders are able to carry produce to the city per unit time, and this is what they've got to carry from the farmers. So you need enough traders to carry that amount. So we can write then that NTW over 2R equals N kappa P. And we can solve this to give NT in terms of the number of farmers N. So that comes out to be 2 kappa P R over W times N. And now next we define the population density rho. That's the population density of farmers. So the total number of farmers is going to be the population density times the area, which is pi r squared. So N is equal to rho times pi r squared. Let's put it the other way around. And so that means that we can substitute for r here. If we write that r, solving this equation, it gives us r equals the square root of n over pi rho. So that nt, putting that up into there, gives us 2 kappa p n to the 3 halves, because there's an n there, and then there's a square root of n, n to the half, so that gives n to the 3 halves over the square root of pi rho. And we've now got then this formula for NT in terms of N, and we've got this formula for NA in terms of N. So we know the total population of the city in terms of N. And Graszewski suggests that the government makes a profit from this produce that's being brought into the city minus the amount that's needed to feed the city population. So there's a lot of produce coming in, but there's more potentially than is actually needed by these artisans and traders, and the difference is the government's profit. So the government's profit is going to be the amount of produce arriving into the city, which we've got up here somewhere. The produce to the city per unit time in terms of N is NKP, and then we've got to subtract from that the amount spent on food for the NA plus NT. So it will be, we can write that as C, if C is the amount of food consumed per unit time by one of these workers, C into NA plus NT. And so we can substitute our NA and NT into here. So that is equal to N kappa P minus C into NA was sigma N plus NT is this. And we can then multiply all that out and do some gathering of terms, and we can write that as G, well, the government profit, we'll call that G, is equal to an minus b over w root pi rho n to the 3/2. And what we've done there is we've simplified some of these constants down into new things we've called a and b, where it turns out that a is equal to kappa p minus sigma c, and b equals 2 kappa p c. And these things, the kappas, the amount farmers can produce per unit time, the amounts they're prepared to trade, the amounts of artisans per farmer, and the amounts of food consumed per workers, he's put all those lumped together into these constants because they're things that don't really change, aren't particularly variable, but we are interested in things like W, how fast the traders can travel, because those will vary according to the terrain, as we said, and also the population density rho will also depend upon the terrain, whether the land is more or less fertile. And so we have here an expression for G in terms of N. This is how much profit the government can make. And for a given situation, a given population density and a given values of W, V and L, the speed and the load for the traders, Reshevsky proposes that a government would try to maximise this. It wants to maximise the amount of profit it gets out of this trade. So to do that, we differentiate this equation with respect to n and set it to 0 to find the maximum. So we're going to find dg by dn equal to 0, set it equal to 0, and solve for n. The n that makes that dg by dn equals 0, that will be a maximum. We covered that again in the mathematics module on calculus. And I'll have to start up here, so let me just get rid of some of this. So what we're doing is finding dg by dn, set it to 0 and solve for n. And I won't go through doing that, but we should know how to differentiate this. You know, dg by dn, this will be just a, because when we differentiate that, the n disappears. And this will be 3/2 times this to n to the 1/2. And we then solve that equation for n. And what we find when we do that is that the optimum value for n, the value of n that maximizes this, which I'll call n star, is equal to 4 pi a squared omega squared rho over 9 b squared. And then we've got the city population, is what we're really interested in, which is going to be the optimal maximum value of NA and NT, or the values of NA and NT when N is at this optimal maximum value. And we know how to work out NA and NT. Well, I've wiped it off NA, but NA was equal to sigma n, and NT was given by this. So we can substitute that n star value into this equation and into the one for NA, add them up, and we'll get the population of the city. And it comes to something fairly horrendous, which I shall write up. Okay, it seems to come to that. 4 pi a squared into 4 kappa p a plus 3b sigma or over 27b cubed all times omega squared rho. But the key point here then is that NC star is a function of rho and omega squared. That's how they enter into the size of the city. So as both rho and omega squared increase, so does NC star increase, so does the optimal city size. And so one thing is then that if the population density is greater, so more fertile territory, more people per square mile, then you'll find that the cities are larger. And if omega squared is large, then also the cities are going to be larger. And in fact, an increase in omega by a certain amount has a strong effect on NC because it's omega squared. And omega, remember, is equal to VL. Well, that's VL squared. So if either speed increases or the load per trip increases, then this will increase at the rate of a square of that, and that will increase the city size. Well, both of these are larger for sea trade, because although a ship travels at a fairly sedate rate, it travels 24 hours of the day, and it certainly carries a much larger load than a horse and cart. So if you think about, old times, so V and L tend to be larger for sea. Well, again, a modern super tanker can carry far more than a truck going down the motorway. So the conclusion for that, says Reshevsky, is that ports are large. We would expect ports to be larger than other cities because their W, the transport that they're using by sea, it has this larger value of W, which therefore increases the value of the city size. So ports we should expect to be particularly large among cities. And then Reshevsky thinks beyond this model by suggesting that the traders here, instead of going to and from the farmers in the fields, could be trading with other cities. So they're travelling to other cities. So we can use this to think about modelling intercity trade. And in that case, when they're travelling to other cities, the distance that they have to travel, which here is the radius of the hinterland, would now be the spacing of the cities, the typical distance between cities. And we have rho entering the size of the city here, the population density, because a higher population density means a shorter hinterland to get a particular number. You're packing people into a smaller space, and that means that the trips per unit time of the traders are higher because they don't have so far to travel. And so if we're thinking about intercity trade, a similar thing applies. If the cities are close together, then the traders can make lots of trips, and the optimal city size can be larger. So where cities are more closely packed, we would expect to find them also to be larger. Now, to be closely packed, they have to be able to have sufficiently sized hinterlands, but assuming the population density is large enough that the cities can exist within a concentrated area and so be closely packed, then we would expect them to be larger through this intercity trade. That's one conclusion. And another point that he suggests is that traders, the number of traders you get is going to depend upon how lucrative your trade is. So he suggests that if the cities are closer together, then we said that the traders can make a lot of trips per unit time. They're going to make a lot of profit per unit time. And so he suggests in that case you'd expect more people to move into trade because of the profit opportunities. So he suggests that where cities are close together, they'll not only be larger, but you'll find a larger proportion of the population engaged in trade. And equally, where there's better transport, so that the traders can move more quickly, so the speed at which they're travelling, is higher. Again, that will allow them to make more trips per unit time, and that will also increase the fraction of traders in the population, because there are lots of lucrative opportunities if you can make lots of trips and make a profit on each one. So those two things, the spacing of the cities, the closer they are together, the more that society will be engaged in trade, and also the better its transport, the more roads or rivers, canals, whatever, or seagoing opportunities. But the better the transport, the more of a trading nation that society will be, higher proportion of traders in its city populations.